It's time to find out if the odds are really in our favor. In this episode, we discuss the basics of probability because this is the foundation for totally doable stats. So, in previous episodes, we discussed measures of descriptive statistics, simply describing data. Now it's time to turn our attention to more powerful statistics that allow us to work from a smaller sample and possibly infer our findings back to the larger population we're studying. These inferential statistics are founded upon the mathematics of probability. Simply stated, probability is the mathematical likelihood that a particular event is going to occur. More specifically, we're investigating expected relative frequency probability, but we'll just call it probability. Probability is fairly easy to calculate. It's just the number of successes divided by the number of possible outcomes. For example, if I were rolling a single die and I wanted to know the probability of rolling a 3, I would take the number of ways to successfully roll a 3, 1, and divide it by the number of possible outcomes when rolling a single die, 6. So as you can see, the probability of rolling a 3 is somewhere in the neighborhood of 1 over 6, which is 0.1667 if I convert it into a decimal, which is what I would do most of the time if I'm talking about probability. Now this is fairly simple if I'm looking for one possibility. If I was looking for the probability of rolling a 4, I would have exactly the same number, one option out of 6. By the way, if I was converting this into a percentage, then I'd simply take this number and multiply by 100, which tells me that if I wanted to know what is the percent chance of rolling a 4, well, then it's going to be somewhere in the neighborhood of a 16.67 or 16 and 2/3% chance of rolling a 4. And that's all pretty straightforward and pretty easy to see. So why don't we take a look at a little bit different example. What if I wanted to know what it would be like to work with 2 dice? What if all of a sudden I had 2 dice to roll at the same time, and so I've got dice number 1 and I've got dice number 2. Well, I can pretty quickly think through what are all the possibilities. I can think that if I'm rolling 2 dice, I can roll a 2 or a 3 or a 4, all the way up through rolling a 12. Those are the possibilities I've got. But it starts to get a little more complicated, right? Like if I think about the probability of rolling a 2, where there's only one way to do that, I'll roll a 1 with each die. But if I think about the probability of rolling a 3, well, there I could roll a 1 with the first one and a 2 with the second, or a 2 with the first one and a 1 for the second. So there are actually 2 different ways I can roll a 3. When it comes to rolling a 4, I could roll a 1 and a 3, a pair of 2s, or a 3 with the first and the 1 with the second. If I want to know about rolling a 5, again, I can go a 1 and a 4, 2 and a 3, 3 and a 2, or a 4 and a 1, and so on until I've got the entire list of possibilities, which is actually 36 different possibilities. So this means that the odds here of rolling a 6 would be 5. So I'd write that the probability of rolling a 6 would actually be 5 out of the total possibilities, 36. And so if I calculate each of these out, I think it's easier to see instead of me writing it out. Let's switch over to looking at an Excel spreadsheet. I've built an Excel spreadsheet that accommodates the idea of dice rolls for 2 dice. And here, over here on the right side at theoretical probabilities, we can see the probability of rolling each one of these numbers. What's interesting is if we look down here at the curve, we find that the probabilities for rolling each of these numbers kind of starts to look like it would fit under a normal curve. This is part of what can help us to understand how sampling allows us to approximate some things about the population. If I have a very small sample, like over here on the left, I've got an example from 10 dice rolls, and I've got each of these sets of random, so all I have to do is click and it'll show us 10 different rolls. You can see that in this chart over here on the left, it doesn't really line up with being normally distributed. But what if I all of a sudden increase it to 30 dice rolls, or 500 dice rolls, or even 10,000 dice rolls? Now all of a sudden, it's starting to look more like what I would expect, the theoretical probability. What I'm seeing is the more I have in my sample, the more it starts to look like the population. And so as we move forward in following videos, we're going to see that as long as we follow some rules about how we do sampling, as far as sample size goes, as far as random selection goes, things like that, we can start to estimate from a smaller sample what the entire population might look like. Now that we've taken this first look at probability, my hope is that you recognize that these are also totally doable stats.